In a previous screencast, we talked about how and why ions form. Just as a quick review, we learned that metals typically are going to lose electrons to form positively charged cations, and we learned that nonmetals are going to gain electrons to become negatively charged anions. The reason why this occurs is due to the octet rule. If you look at this image of sodium on the left, we can see that in sodium's outer energy level, known as its valence shell, its valence electrons, it only has 1. Due to the octet rule, it wants 8. So it has 2 options. It can gain 7, or it could lose 1, thus exposing the next shell down. It's going to be a lot easier for sodium to lose 1 electron to expose that next energy level down, which has 8, and than it will be to gain 7. So that's what sodium does, as well as all other metals do, is they will lose their outer energy level electrons to expose their next layer down, which is going to have 8, and thus achieving 8. For nonmetals like chlorine, nonmetals typically have more electrons in their outer energy level, in their outer valence shell. In this example, chlorine has 7. Chlorine wants 8, so it needs to gain electrons to become satisfied with its octet rule, to have a full batch of 8. So instead of losing electrons like metals would, it's going to be easier for nonmetals to gain them. So that's what they do, is they gain electrons to become negatively charged anions. If you look at this abbreviated periodic table, we can see that we have the first 4 periods, or first 4 rows of the periodic table shown, as well as the representative elements, so all of our A elements. So group 1A, group 2A, group 3A, all the way to group 8A. So on a periodic table, these are columns 1 to 13, 14, 15, 16, 17, and 18. And so as you can see, as we move down the periodic table, we are adding more of those energy shells, more of those layers of electrons. But the trend that you will find is that all of the elements in group 1 have 1 valence, or 1 outer electron. For all the elements in group 2, they all have 2 outer electrons. Group 13, they all have 3. Group 14, they all have 4. 15, they all have 5. 16, they all have 6. Group 17, they all have 7 outer electrons. And then group 18 has full octet 8. So that's why the noble gases in group 18 do not react, is because they're already satisfied with their full octet. You'll notice that smaller atoms, like ones in group 1 and 2, can be satisfied with, or I shouldn't say groups 1 and 2, I should say just the period 1. So smaller atoms like hydrogen, helium, boron can be satisfied with 2 electrons in their outer energy level. We call that a duet. But for the most part, that is just an exception, and we're always going to be seeking to have a full octet 8 electrons in the outer energy level. So based on the location on the periodic table, we can make predictions as to what types of ions are going to be formed by the various types of elements. We just need to know how many electrons that they have in their outer energy level, and from that we could determine how many they're more likely to gain if they are nonmetals, or lose if they are metals, and then we could assume what charge they will take. And so since all of the alkali metals in group 1A have 1 valence electron, they want to lose that 1 electron to become stable. And so when they lose that electron, they form a positive 1 charge. Group 2A, group 2, they all have 2 valence electrons, so they want to lose those 2 valence electrons to become a positive 2 charge. So I could predict that all of the elements in group 2, beryllium, magnesium, calcium, and so on, will form positive 2 charges when they ionize. Group 3A, these metals, they want to form positive 3 charges. When you get to group 4, for carbon, it has 4 valence electrons. It can either lose 4 or gain 4. So carbon can actually form 2 different versions of ions. It can form a positive 4 ion if it's going to act like a metal, or it can form a negative 4 ion if it's going to act like a non-metal. Group 5A, group 15, they have 5 valence electrons, so therefore they would rather gain 3. So this time, now that we're dealing with nonmetals, we're gaining electrons. And so instead of losing electrons and becoming positively charged cations, we're gaining electrons to become negatively charged anions. So nitrogen, phosphorus want to gain 3. When they gain 3, they form a -3 charge. The chalcogens, oxygen, sulfur, selenium, we have 6 valence electrons, so we need to gain 2. So these form -2 charges. And then your highly reactive halogen gases, they all have 7 valence electrons. They just need 1 more. They're going to gain that 1 extra electron, form a -1 charge. And so we have this trend in the periodic table where metals on the left form positive ions based on the family that they're in. So the alkalis form +1 charges, the alkaline earth metals form +2s, the trials, group 3A, form +3, group 4A, the tetrals, you have carbon can go either way, forming a +4 or a -4. Silicon, germanium being metalloids, they're going to typically, well, silicon more often than not is going to act as a non-metal, but it can act as a metal as well because it's a metalloid. For group 5A, so following the trend, we have -3 charges. 6A, group 16, -2 charges. Fluorine, chlorine, bromine, the halogens, -1 charges. And then group 18, group 8A, they already have a stable outer valence electron shell, and they're not going to gain or lose, so they're not going to ionize. So their charge is 0 because they remain neutral. So when we have substances, when we have elements that ionize, we form these positive and negative ions, and these positives and negatives attract each other through Coulombic interactions, so electrostatic interactions, and we call that ionic bonding. So when you have a positive bonded to a negative, it's kind of like magnets linking together. That is an ionic bond. Here we can see potassium, 1 extra electron. It's losing its electron to iodine, which is actually taking it. Iodine had 7, needed 8. Potassium had 1, needed to lose 1 to gain or to expose that next layer down, which has 8. And so potassium loses 1 to get 8. Iodine gains 1 to get 8. And so they both become stable by transferring 1 from potassium to iodine. When that occurs, potassium forms a positive charge, iodine forms a negative charge, and they are electrostatically attracted to one another. We call this an ionic bond. Ionic bonds are created when electrons are transferred, creating ions. Here's another example. Magnesium has 2 electrons to lose, and then we have chlorine, which has 1 electron to gain. Instead of chlorine taking both of the electrons from magnesium, because chlorine only needs 1, we'll actually have another chlorine atom come in and take the second electron from magnesium. Magnesium has 2 in the outer energy level. It's going to lose those 2, and when it does, it forms a +2 ion. Well, where do those electrons go? Well, 1 chlorine took 1 to get 8, forming a -1 charge. Another chlorine came in and took the other one to get 8 to form a -1 charge. So therefore, we have 3 atoms interacting with this transfer. So magnesium ends up with a +2 charge. Each of the chlorine ions or chloride ions end up with a -1 charge, and then the attraction exists between the +2 charge of the magnesium and each of the chlorides with a -1 each. And so we have 3 ions being attracted to one another in a 2-to-1 ratio. So whenever we have electrons being transferred or shared, we call that a chemical bond. So chemical bonds are forces that hold atoms together. There are 3 types of chemical bonds, and the type of bond is dependent on what's going on with the electrons. In what we just talked about, we were transferring electrons. This typically occurs between metals and nonmetals. Metals have a tendency to have a few extra electrons and they want to lose them to become positively charged cations, and nonmetals are just down a few electrons and they want to gain some to become negatively charged anions. So transfer occurs and there's an electrostatic attraction. That's an ionic bond. There's another type of bond called covalent bonds. These typically occur between nonmetals and other nonmetals. Since there's not one entity, there's not a metal present that has a couple extra electrons to give up. Instead, what these nonmetals do, since they both need a few electrons to become stable, what they do is they share their electrons. And in that fashion, they become stable. We'll take a closer look at this in a bit. And then there's the third type of bond, which is a metallic bond. Metallic bonds are between two metals, where there's no species that just needs a few more. All of the cations, all of the atoms have extra. So what they do to deal with that extra is they pull them all together and the electrons get delocalized. So the key things to take away from this slide are that covalent bonds are between nonmetals and other nonmetals. Ionic attractions, we'll call them, or they're technically bonds, but there's no actual bond being created. It's more like a magnetic electrostatic attraction. Ionic bonds are between metals and nonmetals, and the metallic bonds are between metals and metals. And so very easily we could determine a bond type just by analyzing whether we have a metal or a nonmetal interacting. If we want to be more precise, we could talk about what's going on in the interaction, in which case covalent bonds, electrons are being shared. Ionic attractions, electrons are being transferred completely, and metallic bonds, electrons are being pulled. And going even further, we can analyze how those electrons are going to interact between the two elements. And we'll cover polarity in a little bit later in this lesson. So let's go back to covalent bonds. So we talked about ionic bonds and the transfer electrons causing electrostatic attractions. For covalent bonds, these are the ones where we have nonmetals and nonmetals. Remember, nonmetals, they just need a few more extra electrons to get their full octet. Well, if there's not a metal present to donate electrons to them so that they could become satisfied, what nonmetals can do is they can share electrons with each other. And so here we have an example where oxygen, it has 6 outer electrons and hydrogen has 1 each. Hydrogen being one of our exceptions, being small, it can be satisfied with 2. Oxygen being bigger, needing 8 to complete its octet. So oxygen, nonmetal, needs to gain some electrons. Hydrogen, also nonmetal, needs to gain some electrons. There's no metal present to donate their electrons, so therefore what happens is hydrogen comes in and shares an electron with oxygen. So hydrogen is satisfied by having its electron plus a shared one with oxygen, so hydrogen's happy with its duet. Oxygen is going to be happy because it has its 6, then it's going to share one with one hydrogen and share one with another hydrogen, thus getting its 8. So that's how we end up with 3 satisfied atoms here. Oxygen has 8 electrons, each hydrogen has 2 electrons. Sometimes these nonmetals have to share more than 1 electron at a time. And when they do that, they create what we call multiple bonds. And so in this case, if we have 2 oxygen atoms, if they go in and share just 1 electron each, they still aren't going to be satisfied. They're not going to have 8 electrons. They're going to have 7 because they start off with 6. If they share 1 within another oxygen atom, they'll just have 7. But if they share 2 with another oxygen atom, then they'll have 8. And so when we're sharing 2 electrons at the same time, we call that a double bond. If you look at the same example with nitrogen, nitrogen starts off with 5, it needs 3 more. Well, sharing 1 or 2 is not enough. It has to share 3 different electrons with another nitrogen to create what we call a triple bond. The more covalent bonding you have, the stronger the bond system will be. So a single covalent bond is the weakest of all the covalent bonds. A double covalent bond is stronger, and then a triple covalent bond is stronger yet. Remember, covalent bonds are formed when electrons are being shared, whereas ionic bonds are created when electrons are transferred, and then we have an electrostatic attraction. So this just goes to show you how the triple bond is formed between 2 nitrogen atoms to create a nitrogen molecule. And so we can determine the type of bonding that's present and to the extent in which it's going to occur using electronegativity. So what electronegativity is, it's a measure of the ability of an atom to pull electrons toward itself through a chemical bond. bonding, the bond type is always determined by the electronegativity. And so what we see is that whenever we have two atoms that have very different electronegativities, that's when we have the transfer of electrons. And that's when we create those ionic bonds. Whenever we do not have a very big difference in electronegativity, then we, instead of transferring electrons, we're just sharing electrons. And then there's two forms of sharing electrons. We could have even sharing, where the electrons are going to be near the atom an even amount for each atom that's present in the compound. And then we also have an uneven sharing, where electrons will be around one atom more than the other. So if you look at this image, we have we're talking about electronegativity differences here. And so whenever electronegativity differences are great, we see the distance. So we're representing the distance by the base of the pyramid. And so a big difference in electronegativity will be the larger base of the pyramid. But as we go up this pyramid, the difference between electronegativities will decrease, and we have these different ranges. And so when we have a big difference, we call those ionic bonds, because the difference is so large that electrons will be transferred from one to the next. When the difference is not that great, you can kind of think of it as a tug of war. If both combatants are evenly matched, one's not going to very easily pull the other one. Okay, well, if the electronegativity, so going back to that example, going back to ionics, if you have a tug of war battle and you have a really big strong guy, and then they are playing tug of war against someone that's very frail and weak, they're going to very easily pull that person. Well, that's just how it happens with atoms too. If they have a very large electronegativity, they could very easily pull those electrons towards themselves. And so much so that they're transferring the electrons to themselves. And so remember, nonmetals want those extra few electrons. So that's where electrons are going to, is they're going to the nonmetal. So therefore, the nonmetals are the ones with the greater electronegativity, and metals have smaller electronegativities. And so if you have two elements that have similar electronegativities, or even the same, in the case of like nitrogen forming N2 or oxygen forming O2, the electronegativity difference is 0 between them, because electronegativity is the same for all oxygen. It's the same for all nitrogen. And so if we have no electronegativity difference, there's no transfer of electrons. Instead, it's just a perfect sharing. Whereas if it's somewhere in between the complete transfer and the equal sharing, we have an unequal sharing. And so an unequal sharing would be, you have an atom that has a relatively high electronegativity, and then another atom that also has maybe a medium electronegativity. That difference in electronegativity is not great enough to transfer the electrons, nor is it going to be an equal sharing. So what we call that is polar. So something that is polar means that we're going to have electrons grouped around one atom more so than the other atom. And so if you look at these three matching images, we could see the nuclei represented by these black spheres, and then we have these electron clouds. So this top one, we have equal sharing of electrons. We see the electron clouds are about equal in size, which tells us that the electrons are spending the same amount of time around each nuclei. In the middle one, this is the one that's unequal sharing. This represents a polar substance. And so we have the electrons spending more time around the nucleus on the right than the one on the left. This is going to be due to the polarity. Electrons are more attracted to the one that has the higher electronegativity than the one that has the lower electronegativity. And then finally, when the electronegativity differences are substantial, we have a complete transfer. And so this bottom image, we could see that all of the electrons are grouped around the right nucleus and barely the left. So electrons must have been transferred from the left, which would be a metal, to the right, which would be a nonmetal. And so bonding, it's not just this or that, it's more of a spectrum. A spectrum between nonpolar covalent, where we have equal sharing, all the way to, it goes beyond sharing. It's an absolute theft, a transfer of electrons, and that would be ionic. And so electronegativity is a quality that is specific to each type of, or each element on the periodic table. And what we see, so this periodic table is nice because it represents the electronegativities by both the darkness of the green color as well as the height of the stack for the element. And like I mentioned, nonmetals want to gain electrons. So since nonmetals want to gain electrons, they're more likely to have greater electronegativities. They have a greater propensity to take electrons away from other things. They have a greater ability to pull electrons toward themselves. The metals, the ones that are desperate to lose the electrons, they're fine with losing their electrons, because when they lose 1, 2, or 3 electrons, they're exposing their next layer down and they get a full octet that way. So metals, they want to lose their electrons. And since they want to lose their electrons, they don't have that great of ability to pull electrons toward themselves through a bond. So therefore, they have very low electronegativities. So we see electronegativities are low on the left side of the periodic table where our metals are, because those are all species that want to lose their electrons. And then the electronegativities are large on the right side of the periodic table where we find our nonmetals, because our nonmetals all want to gain electrons, and so they have the ability to pull electrons toward themselves through the bonds. Okay, so we'll see that electronegativity is going to be a range of 0.7 to 4. 4 is the maximum, and so fluorine has the greatest electronegativity. So as we move away from fluorine on the periodic table, electronegativity decreases. And so you don't even need an explicit value for electronegativity to be able to compare two elements. Just by virtue of their position on the periodic table, we know that fluorine has a greater electronegativity than sulfur, which is catty-corner to it, just because fluorine is the highest, and as we move away from fluorine, it's going to decrease, and that's the general trend. So, because when molecules form, they are made with covalent bonds, that tells us that we have an unequal sharing. And so here we have hydrogen chloride. Hydrogen chloride is a covalent bond. I know it's a covalent bond for a couple of reasons. Firstly, I have hydrogen and chlorine, both nonmetals. When I have a nonmetal bonded to a nonmetal, that creates a covalent bond, and that tells me that the electrons are being shared. However, hydrogen and chlorine have very different electronegativities. If I were to look at my chart here, hydrogen has an electronegativity of 2.1. It's up here on the right. And chlorine has an electronegativity of 3.0. So that's a difference of 0.9. And so this is the way you would find this is how you would more precisely find the bond type. So 3.0 minus 2.1, I'm subtracting the electronegativities. And if I go back a couple slides, I could see my electronegativity ranges. So 0.9, that falls into the covalent bond range. So that is between 0.4 and 1.7. So that tells me that I have an uneven sharing. So that's going to form a polar covalent bond. And so I knew it was a covalent bond because I had a nonmetal and a nonmetal, and I could also determine that it's a polar covalent bond because chlorine's electronegativity is far greater than hydrogen's. 0.9 is the specific amount that it's greater, and so using a chart I can classify it as a polar covalent bond. If the electronegativities were very similar in size, then I would just say that it's an equal sharing of electrons, and it would be a non-polar covalent bond. And so we have polar molecules where we have an unequal sharing. One has a greater electronegativity than the other. And we have non-polar molecules where it's a roughly equal sharing, where the differences are not that great. So water is widely considered a polar molecule because not only does it have one polar bond between the hydrogen and oxygen, it has two of them. So it has two different polar bonds. What makes it a polar bond? It's the difference in electronegativity. Oxygen has a much higher electronegativity than hydrogen. I know that water is a covalent substance because I have hydrogen, a nonmetal, oxygen, a nonmetal. Go back to my electronegativity table. Hydrogen has an electronegativity of 2.1. Oxygen has an electronegativity of 3.5. 3.5 minus 2.1, I have an electronegativity difference of 1.4. An electronegativity difference of 1.4 is on the higher end of the polar covalent range, so therefore water, each bond in water, so one bond between the hydrogen and the oxygen, that's a polar bond, and then it also has another polar bond. So since water has two polar bonds, it is definitely a polar substance. Go back to that slide, and that's actually the last slide. So important vocabulary terms for this section: we need to know what an ion is. We need to be able to compare ionic bonds with covalent bonds. We need to know what molecules are. the difference between polar molecules and nonpolar molecules, as well as polar and nonpolar bonds. It all goes back to the electronegativity. If you're going to have one main thing in your notes, it's going to be this table right here. This table highlights the differences in covalent and ionic bonds, as well as metallic. Covalence between two nonmetals, metallics between two metals, ionics between a metal and a nonmetal. It tells us what's exactly happening with the electrons. Covalent bonds, the electrons are being shared. Ionic bonds, electrons are being transferred. And metallic bonds, electrons are being pulled. And then if you want to get really specific with the polarity, you could just look at the electronegativities. The greater the difference in electronegativity values, the more likely it's going to be polar. If it's just an uneven sharing and it's polar, we call that polar covalent. If it's extremely polar, so polar that it's actually transferring electrons, we call it ionic. And if it's one is hardly greater than the other, we call that nonpolar, and that's an equal or even sharing. So that's it on bond types. I hope that you found this screencast helpful.